This is section 1.1.3 for Principles of Engineering, covering the topic of gears, pulley drives, and sprockets. This is part 1 of the video. It's about a 10-minute video that covers just specifically gears and gear systems. Gear systems change the speed of rotation, they change the direction of rotation, and they change the amount of torque available to do work. Torque is a twisting force. It's important to keep in mind that a gear train is a mechanism that's used for transmitting rotary motion, or a twisting motion, spinning motion, and a torque through interlocking teeth. A gear train is made up when you have 2 or more gears that are meshed. The driver causes the motion, and the motion is transferred to the driven gear through other gears or through just the driver gear. Mating gears always turn in opposite directions, as you can see from the top blue and red gears. The idler gear, like the one down here in the middle, allows the driver and driven gears to rotate in the same direction. Mating gears must always have the same size teeth, or what they call the diametric pitch. RPM stands for revolutions per minute. It's how many times you get a full spin out of a gear, out of anything actually. And when we're looking at 2 gears that are mated together, for instance the red and blue gears here, the larger gear always moves slower or at fewer RPMs than the smaller gear. Gears that are locked together on the same shaft are always going to move in the same direction and at the same RPM. Here's a list of a few variables that you need to know when it comes to gear ratios and gears. N stands for the number of teeth, D is the diameter, this is a lowercase rho, or a Greek letter rho, which stands for angular velocity or speed, which we call RPMs, and this fancy looking T is considered for torque. When we look at, for instance, this red side here, we're looking at the red gear. The subscripts N mean that that is my driver gear. Out, in this case, means it's my driven gear. So the driver gear has 6 teeth, 2-inch diameter, spins at 40 revolutions per minute, and has 40 foot-pounds worth of torque. My driven gear has 12 teeth, it's 4-inch diameter, 20 revolutions per minute, and it has 80 foot-pounds of torque. All but the amount of torque is listed up here on this picture up in the upper right-hand corner. Some equations to know for gear ratios, and these equations are ones you want to have easy access to at any point in time. This is a good point to pause and write what all of these are down, as well as write what their definitions are, what they stand for. Gear ratios we always write as over 1. So a gear ratio over 1 we say is the number of teeth for the driven gear over the number of teeth for the driver gear, and that's equal to the diameter of my driven gear over the diameter of my driver gear, which is equal to the speed of my driver gear over my driven gear, which is equal to the torque of my driven gear over the torque of my driver gear. It's a big mouthful to say, but what's nice is they work out equal, and these are nice easy equations to work. So in the case of our example, I have the number of teeth out, which is my driven gear, 12 teeth. If I go around and count, there's 12 teeth on the blue gear there, over 6 teeth. If I look at my diameter, I get 4 inches over 2 inches, 40 revolutions per minute over 20 revolutions per minute, and per the previous slide, we had the 80 foot-pounds of force over 40 foot-pounds of force, which gives me a gear ratio of 2 to 1. In the case of this next example, we're going to look strictly at teeth, so I'm looking at my in-out over in-in formulas. What's important to remember is when I'm given an example of this, what is the gear ratio between gear A and B? Gear A would be my driver gear or my in gear. Gear B would be my driven gear or my out gear. So to find the gear ratio, which I need to write over A1, I have my driven gear teeth over my driver gear teeth. In this case, it's 12 over 20 gives me a 0.6 over 1. If I want to know the gear ratio between B and C, C being my idler gear, it is just there to change the direction of gear D when I get to that. So I have B as my driver and C as my driven, so I have 5 over 12, and I get a 0.42 over 1. If I want to know the gear ratio between gear C and D, I have 20 over 5, which gives me a ratio of 4 over 1. It's important to remember that idler gears don't affect the gear ratio overall. And if I want to know the total gear ratio for the train, I multiply all three of my gear ratios together, from A to B, from B to C, and from C to D. In this case, and only in this case, because of the way they set up the example, I get a total gear ratio of 1 to 1. So if I want to know if gear A and gear D were directly together, cutting out both gears B and C, I want to know what the gear ratio would be. I have my driven, or my output gear, which is D, over my driver, or my input gear, which is A. So I have 20 teeth over 20 teeth. I get 1 over 1. If I change the last gear over here to have 40 teeth, I would have my out is 40 over 20, and that's what this over here on the right is. Or I could just change that very last gear ratio from C to D, but either way I still get a gear ratio of 2 over 1. Gear ratios with compound machines are just very similar to figuring out mechanical advantage for both simple and compound machines. When I look at forces, for mechanical advantage, I have my force out equal to my mechanical advantage times my force in, which is the same thing as saying FR over FE. When I'm talking about gears, I have my torque out equal to my gear ratio times my torque in. In a compound machine, just like in a compound, when I'm looking at compound gear ratio machines, I just multiply each of my different items together to get my final mechanical advantage or my final gear ratio. But keep in mind that we're talking about forces with mechanical advantage, and we're talking about torques, which are a twisting force. It is very different from a standard force. In this next example, we're looking at a compound machine that has 3 different mechanisms. I have a wheel and axle, which is up here with the purple gear, and my force of effort, which is where my initial force is going in. I have a gear train between the purple and the blue gear, and then I have a wheel and axle here at the end, which is where my force of resistance is coming out. To find out my mechanical advantage and the gear ratio of each individual piece, I do it the way we did before. I know my distances, so I have my distance of effort over my distance of resistance. My distance of effort is my 4 inches. The distance of resistance in this case is my 1.5 inch diameter of the gear. So when I look at my gear train, I have my gear train is my total of teeth out over my total of teeth in. My out would be 24 teeth and my in would be 60 teeth, so I get a gear ratio of 0.4 over 1. To look at my final machine, which is another wheel and axle, we have our distance of effort, which is 0.6. That's where the effort's coming into this last machine. It's coming from the purple wheel to the blue wheel. The blue wheel has a diameter, or a radius, of 0.6. 0.6 over 4 gives me 0.15. So if I look up my total mechanical advantage, I look at the mechanical advantage of both the wheel and axle. So it was a 2.67 times 0.15 gives me 0.4. Gear total ratio is just between the two different gears, and that's a 0.4. We're almost finished with gears. If I look at a compound gear train, we have a driver gear. In this case, it's my green gear. That is meshed or mated with the yellow gear, and it's a little harder to see for you all, but the yellow gear is moving much slower than the green gear is, at a far fewer RPMs. We attach our blue gear on the same wheel and axle, so the RPMs of the blue gear is exactly the same as the yellow gear. Finally, I throw my last gear in and mate it or mesh it with my blue gear, and that's the red gear that's shown there, and it is moving much slower than any of the gears that are currently up on the screen. As I've already said, the two middle gears share a common axle, so they rotate at the same speed, but this allows the final gear to move much slower and produce a lot more torque or a lot of force. The fact that the driver gear is moving very fast transmit the forces through it through different distances and gear ratios, so that last red gear can have a lot of force behind it and it can move much easier. So if we look at actual compound gear ratios, in the case of all of our different gears here, if I want to know the gear ratio between gear A and B, gear A would be my driver gear, as I said on the previous slide. Gear B would be my driven gear. So the gear ratio between gear A and B in this, I have my number of teeth out over my number of teeth in. So I have 40 over 10, which would give me a gear ratio of 4 to 1. If I want to know the gear ratio between C and D, it gives me 50 over 20, or my out over my in, which is 2.5 to 1. To know the gear ratio of the entire train, I just multiply the two different gear ratios together and I get a gear ratio of 10 to 1.